Good evening, everyone. We are in the week 2 problem solving session of the NPTEL course, Control and Tuning Methods in Switch Mode Power Converters. And week 2 is about modulation techniques in switch mode power converters. I am Teja Golla, a PhD scholar working under Professor Santanu Kapat at IIT Kharagpur. Let me share my screen. I hope you can see my screen. Yes, okay. So today's discussion will be about modulation techniques. So I'll just quickly discuss about the fixed frequency modulation techniques and variable frequency modulation techniques, and each of them has different nomenclature in each of this, like trailing edge PWM, leading edge PWM. So what are these and how to uh, understand the differences between them, and after that we'll solve few problems. So starting with the trailing edge PWM and leading edge PWM. So the name suggests pulse width modulation. So this is pulse width modulation. So what is trailing edge? What is leading edge? So these two are used in both voltage mode control as well as current mode control. So the architecture will be slightly different in the case of voltage mode control. So let us start with VMC, which is voltage mode control. So both has trailing edge as well as leading edge, but the way it is implemented is slightly different. So VMC is voltage mode control. So in the case of voltage mode control, a sawtooth is compared with the control voltage. So the control voltage is the output of the controller. So the output of the controller is being compared with the sawtooth. So how is it being compared, and which sawtooth is selected for comparing with the control voltage decides whether it is a trailing edge or leading edge. So now I'll draw both side by side so that it will be easy to understand. Starting with the trailing edge. Then we have leading edge. Okay, so how is it? Let me draw. Okay, so this is the sawtooth, and in the leading edge, the sawtooth is slightly different. So let me copy paste quickly, and then, or let me draw it again. That would be good. Yeah, yeah. So as you can see, the sawtooth is different in either of these cases. Now I'm considering the control voltage to be something like this. Yeah, and then now let us draw the gate pulse output of this. Okay, so yeah, so in this case, when the control on the left hand side or on the right hand side as well, when the control voltage is higher than the sawtooth, then the output will be 1, otherwise it will be 0. So if we draw the gate pulse, it will be something like this. So whenever the control voltage is high, then it will be 1, otherwise it is 0. So here also similar. Okay. So why the names trailing as well as leading? So if you see on the case one, which is the left hand side, the edge, basically we are talking about the sawtooth. So in any case, when we look at the name trailing as well as leading, we are talking about the sawtooth. So if you see on the first case, the sawtooth is starting at a value lesser than the control voltage. So that's why it is trailing. Whereas on the second case, the sawtooth is starting from a value higher than the control voltage. So it is above the control voltage. So it is leading. So that's why the names. So in the case of trailing, it will start from zero because it is trailing. Whereas in the case of leading edge, it will be starting at a higher value. So that's why it is called leading because it is leading compared to the control voltage. So the edge means here sawtooth. So the sawtooth is trailing in the first case. So that's why it is called trailing edge modulation. And in the second case, it is leading. So that's why it is called leading edge modulation. Yeah. So in a way, if you see, uh, we are here controlling this region, and in this we are controlling the other region. So it's a different way of getting the duty ratio, but generally in the power electronics we'll be using trailing edge for voltage mode control, whereas in the case of current mode control we'll be using both trailing as well as leading edge, and I'll also discuss regarding that. Since two of the students have come a little bit late, I'll just quickly summarize what I have discussed. So this week is about modulation techniques. So I was planning to summarize the fixed frequency modulation techniques as well as the variable frequency modulation techniques, mainly the nomenclature and how they are different from each other. So I have started with the fixed frequency modulation techniques, the trailing edge as well as the leading edge PWM. These are being used in both voltage mode control as well as current mode control. So the difference is in terms of the implementation. So in the case of voltage mode control, a sawtooth is compared with the control voltage. So this green color waveform is the VCon control voltage, which is the output of the controller. So it is compared in a different way. In the first case, it is starting from zero, so it is below the control voltage. So that's why the edge is trailing. It is called trailing edge. On the second case, it is starting at a higher value compared to the control voltage, so it is leading. So that's why it is called leading edge. So the controller can be implemented in both of these ways, and these are two such cases that we have considered in voltage mode. If you have any queries, you can ask, else I'll quickly move to the current mode control. Any queries so far?
I would like to ask a doubt.
Yes.
Actually, these are the two methods of PWM. Only these two.
Dual edge is also there, where
Okay,
instead of
fine.
sawtooth, we
So
have triangular.
instead of sawtooth, you'll be having a triangular. Fine.
Yes, yes.
Actually, this trailing edge you said for VMC and leading edge for CMC.
No, no, both are for VMC. Now I'll go to CMC and discuss both. The trailing edge as well as leading edge are there in both VMC and CMC. So I'll discuss all the four cases.
Okay, fine, fine. Fine.
Okay.
Yeah.
Yeah. And one nice thing that you have asked also, I would like to point out is in these cases, if you see the time period is always fixed. So what we are varying is the duty ratio, dt. So this is what is being varied. Even in this case, time period is always same because the sawtooth defines the time period, and the sawtooth has fixed time period, and then this dt is being varied. So that's why it is called fixed frequency, because frequency is always fixed and we are changing the width of the pulse, which is the duty ratio. So that's why it is called pulse width modulation, because the width of the pulse is being modulated and the time period is fixed. So that's why the name pulse width modulation. And this is in VMC. Now we'll go to CMC, which is current mode control. So the first question you can ask, why the difference? Like why can't we use the same in both the cases? The reason is in the case of current mode control, we'll be comparing the sensed inductor current with the control voltage, which is already triangular. So that's why we don't need any sawtooth. Whereas in the case of voltage mode control, we need a sawtooth because voltage is not triangular, right? So that's the only reason why it is different for both the cases. Yeah. So in the case of current mode control, I'll be discussing the same trailing edge and then leading edge. Okay, so let me quickly draw the plots. So the same trailing edge means the again here we are discussing about the inductor current. So inductor current is trailing the current reference. So it is below the current reference. So that is the logic. Okay. So here I have considered the inductor current and this is my current reference. Yeah. So this is my I reference and this is my IL. So as you can see, IL is below the I reference. So that's why it is trailing and that's why it is called trailing edge. So the same thing I can do for here, and here the edge is leading means the current is leading, current is above the current reference. So the current reference is at the valley. So let me quickly draw the waveform. Sorry. Okay. So in this case, it will be at the valley. The current reference is at the valley. So this is my IREF and this is my IL. So now, as you can see, this is also called as peak current mode control because I reference is at the peak, and this is called valley current mode control because the I reference is at the valley of the inductor current. So when we are saying peak as well as valley, here we are talking about the current reference. So whether the current reference is at the peak or whether the current reference is at the valley. Here also we are talking whether the current reference is at the peak or the valley of the inductor current. Whereas when we are saying leading edge or trailing edge, here we are talking about the inductor current, whether the inductor current is trailing the reference or whether it is leading the reference. So these are two different nomenclatures that people follow extensively. So sometimes they can say trailing edge current mode control or more famously called as peak current mode control and leading edge current mode control or valley current mode control. So is this clear?
Yes.
Okay. So someone has commented. Yes, sir. Okay. So till now, we have discussed about voltage mode control as well as current mode control. And in either of the cases, time period is fixed and we are changing the duty ratio. And the implementation of this will be done using set pulse as well as SR flip-flop. So we generate a set pulse, we generate a reset pulse. But I'm not going into the details of the implementation because that is covered and I guess that is simpler to understand. So that's why I'm discussing on the aspects which will be confusing or critical so I can solve problems rather than spending the time on teaching each and everything. So I'll explain whatever is important, but if you have doubts, I'll also explain your doubts as well. Okay, so in the current mode control also, the time period is fixed. So in this also, the time period is fixed. And we are varying the duty ratio is the width of the pulse. Duty ratio is varying. And of course, you know, it is from 0 to 1. So the duty ratio can vary from 0 to 1. So that's why these are all fixed frequency modulation techniques because frequency or the time period is fixed. But can I vary the frequency? Yes, we can vary. And there are basically three. One is constant on time, one is constant off time, another one is hysteresis. I'll also discuss the hysteresis. So what is constant on time? The name says the on time is constant. And what is constant off time? The name says again, off time is constant. So in the first case, off time is variable. In the second case, on time is variable. So constant on time. So off time is variable and constant on time is also called valley current mode control. So now by now you know that what is valley current mode control? Leading edge. And then constant off is on time is variable. And then peak current mode control. And then this will be trailing edge. Okay, so what will be the difference? Instead of fixing the time period, we will fix the on time or the off time. So if we are fixing either the on time or off time, who is deciding the other time? Like say for constant on time, who is deciding off time and vice versa. So the off time is coming from the closed loop. Let me draw the diagram that it will be clear. So, okay. So now I'll draw the inductor current. On time is fixed. And then of course the current reference. Okay. So this is my IREF valley current mode, so that's why I have drawn. And then you should be clear with the nomenclature, don't confuse yourself. Even when I started studying, it was very confusing, which is trailing, which is leading. So you maintain how you like, you think in a way that I have taught, so that it will be clear. Whenever we are saying peak or valley, it's about current reference. Whenever we are saying leading edge or trailing edge, it is about the sawtooth or the inductor current. So it will be logical and you will not get confused. So in this case, the on time, which is this from here to here, this is the on time which is fixed. So now who is deciding the off time? The off time is coming from the controller. So whenever the inductor current is trying to go below the I reference, that will be the end of off time. So once it hits I reference, then I'll give constant on time and then I'll wait until it hits the I reference again. So the off time is coming from the loop and the on time is decided by the person who is running the converter. Say on time can be 100 nanosecond, 120 nanosecond. So that is up to the person who is designing the converter. So this is just the opposite of this. Yes. Sorry. Yeah. So here the off time is constant. So we are fixing the off time, T off. And who is deciding the on time? The on time is coming from the loop. Whenever the inductor current touches the I reference at the peak, that is being decided. So I'm trying to maintain the color code same so that it will be easy. This is constant to understand. This is variable. Off time is variable. Here on time is variable. And then that's why they are also called as peak and valley current mode control according to the name. So we are varying either on time or the off time, one of them. Say if we want to vary both, then it is called hysteresis, where we will be fixing both the peak as well as the valley. So now we'll go hysteresis. Hysteresis current mode control. So let us quickly draw the diagram. So here peak and valley are there. So this is I peak and this is I valley. So both are coming from the loop. We don't have control on either the on time or the off time. So both are varying. So this is T on time and then this is T off time. So both are coming from the loop. Whenever it is hitting either the peak or the valley, that decides the off time. So we are not fixing the on time or the off time or the time period. So all are variable. On time is varying, off time is varying, as well as of course time period is varying. So these are the three cases in the case of variable frequency, and then two cases in the case of fixed frequency. Although double edge PWM is also there, but since it is not covered extensively in the upcoming weeks, I have not discussed it here. Whatever is important and critical that I have covered. If you have any questions so far, you can ask. Else we'll start solving the problems. Okay, okay. What about others? Is it clear? Okay. So starting with the first problem, solve the following. Find the on and off times of the gate pulse Q and what should be the value of the voltage V to generate the gate pulse with a duty ratio of 25%. So if you are not clear, this is the voltage V. So in the first question, I'm asking if these are the voltages, what will be the on and off time of the gate pulse Q? And in the second question, to generate a duty ratio of 25%, what will be the value of this voltage instead of 3? So let me draw this again. Before we start, can anyone tell me whether it is trailing edge or leading edge? So when we are talking trailing or leading edge, we are talking about the edge. So you check whether the edge is leading or edge is trailing. So someone
So
has
your reference
commented.
is below the
Yes. So Jinsi Roy is saying leading. What about others?
leading
Leading,
only.
right? Yeah. True. So this is leading because it is starting at a higher value, leading. Purva also says leading. Yeah. So leading is correct. Now let us draw the sawtooth waveform so that it will be easy to solve. So you don't wait for me, you can start solving. I'll also be solving parallelly. Okay, so I have drawn the 5 volt. So this is 5 volt basically. This is 5 volt. I have taken 1, 2, 3, 4, 5 grid so that it will be easy for me to understand. Then this will be, of course, 3 volt. Yeah. So the important thing is to see in the comparator which has the positive sign, which has the negative sign, because depending upon that I will decide whether my on time is this region or this region. Since 5 volt this sawtooth is having positive sign, accordingly my output gate pulse will vary. So we have to be very clear and careful while we are solving this, because the comparator output will change the answer directly. So we have to be careful with this. So has anyone solved? Okay. Anyone? Actually, while drawing the sawtooth, I have made slightly mistake. So yeah, I have not considered the same grid for both. So that's why the gate pulse are not identical, but it's okay. So anyone, what will be the off time and
On
on time of the gate pulse? So this is my Q. What is my on time and what is my off time? Okay. Someone has mentioned on time is zero point 0.4 and off time is zero point 0.6. So Purva says on time is zero point 0.4 and off time is zero point 0.6. Anyone? Are you getting the same answer? So time period is given 1 microsecond. So this is 1 microsecond. So since this is 3 volt, 2 by 3 will be the on time. Sorry, 2 by 5 will be the duty ratio. So it is 2 by 5 into 1 microsecond. So zero point 0.4 microsecond is the on time, and 3 by 5 into 1 micro is zero point 0.6 microsecond, which will be the off time. Yeah. So Purva, you are correct. If I change the plus and minus signs of this, then the Q will be inverted to whatever I'm getting. In that case, this will be zero point 0.6, this will be zero point 0.4. So we have to be careful with the plus and minus signs. So is this clear, everyone? Or do you have any doubts?
Yes, it's clear.
Clear, clear. So now I'm asking what should be the value of this voltage V such that the duty ratio is 25%, which means on time is 1 by 4 microsecond. So my duty ratio is 1 by 4. So anyone, what should be the voltage of this? So for 3 volts, I am getting my duty ratio is 2 by 5. So for V volts, I'll get my duty ratio as 5 minus V by 5, right? So it will be 5 minus V by 5. So if you solve for this, V will be 25%, right? So 5 by 4 is equals to 5 minus V. So my V is 5 minus 5 by 4. So V is 15 by 4. Therefore, my V will be 15 by 4 volts to get a duty ratio of 25%. Clear? Since this is 5 volts and this is 3 volts, my on time is 2 by 5. 2 is basically 5 minus 3 by 5. So I'm considering instead of 3, I'm considering it to be voltage of V. So my duty ratio 1 by 4 will be 5 minus V by 5. So 5 by 4 is equals to 5 minus V, and I am getting V equals to 15 by 4 volts. Any confusion, or is it clear? Can we move to the next problem? This is a simple problem, just we have to understand from the diagram. So you have to check whether in the assignment or question paper minus and plus are the same as what we have solved, or whether it is inverted. If it is inverted, then your answer will be exactly the opposite. So you have to be careful in that case. Can we move to next problem?
Yes, sir.
Okay.
Yes, sir.
Okay. Okay. So now let us go to the next problem. Yeah. So the problem 2 is about RMS current, and I have also given you the formula of RMS current, and it would be good if you remember this rather than deriving it. But since we are solving it, I didn't want you to remember already, so that's why I have given the expression. So I have given an inductor current uh, whose waveform looks like this, and the peak current is 2 amperes. And now I'm asking you to calculate the ILRMS. So can anyone tell me what is the time period of this inductor current waveform?
6 seconds.
Yes. So time period is 6 seconds, right? Time period is 6 seconds. What is T1 and what is T2 and what is T3? Can anyone tell? What is T1? What is T2? What is T3? Also, what is X1? What is X2? What is X3? So Jinsi Joy says T1 is 0. T1 is actually time period, not time instant. So
T1 2 seconds.
yes, very good. T2,
T2 2 seconds.
okay. T3,
T3 2 seconds.
okay, good. And X1, X2, X3 are the values of the inductor current. So basically, I would say, uh, yeah. So from here to here, it is one region. Here to here, it is another region. Here to here, it is another region. So we have to solve for 3 regions. Are you getting? So Jinsi Joy says X1 is 0, X2 is 2. Yeah, very good. So X1 is 0, X1 is 0, X2 is 2, X3 is again 0. So we have to solve for these values. Now we have to substitute. So if I'm not clear, for this time period, T1, this is the region, This is time period T2. This is time period T3. If there is time period T4, then again we'll have T4. And this point is my X1. This point is my X2, which is 2 amperes. This point is my X3, which is 0 amperes. This point is my X1 again because it is being repetitive. So now I have to solve from 0 to 6 seconds, which is my time period. And I think I have made a mistake here. Yeah. So my time period is 6 seconds. So once we get the values, please substitute in the formula given and then please solve. So this is also simple problem. Given you remember the expression for the RMS current, which is also easy. So I have given it for the simplicity, but you have to remember for the final exam. Anyone?
Is it
Okay,
4 by 9?
okay, I have to check the
4
answer.
by
I don't
9?
remember. Okay. So who is this? Jay Lakshmi says 4 by 9. Maybe you can write the answer in the chat and let us see what others are getting. And then I'll also start solving. What about others? Are you able to solve?
It's 2 by 3.
Okay, someone says 4 by 3, someone says 2 by 3. Let us check. 4 by 9 and 2 by 3. Let me check. So I'll substitute the values. So IL RMS square is equals to time period is 1 by 6. Then x1 square is 0. x1, x2 will be 0. x2 square will be 4 by 3 into time period is 2 plus same x2 square is 4, x2, x3 0, x3 square 0. 4 by 3 into time period is again 2. Here all are 0. So it doesn't matter. 0 into 2. So I'll get 8 by 3 plus 8 by 3. So 1 by 6 into 8 by 3 plus 8 by 3 is 16 by 3. So it will be 8 by 9, right? I think someone might
2
have
root
missed
2
one,
by
two.
3.
Yes.
2 root
So
2 by 3.
yeah, very good. So now you have to do the square root of this. So it will be 2 root 2 by 3. I am not solving for the value because that you can calculate it. And whenever you are giving an assignment, kindly check the hint. Sometimes they ask two decimal number, sometimes they ask three decimal number. And then, of course, there will be a range. Say your answer is root 2, which is 1.414. We'll give a range from, say, 1.0 to 1.8. And if we ask you to round it off to two decimals, you have to write 1.41. So you have to be very careful while entering the answer also. And if you enter in a wrong way, then you lose the marks and we can't do anything about it. So carefully read the question. For all the questions where the answer is in terms of integer plus decimal, we have mentioned until how many decimals you have to enter the answer. It is mostly two decimals. So please check the question thoroughly before answering. So is this question clear? Can we move to the next problem?
Yes, sir.
Okay. Yeah. So the next problem is something similar to the gate pulse generation. Consider the following diagram. Is this trailing edge modulation or leading edge modulation? And here I have given the rising slope of the sawtooth is 2 volt per microsecond. Find the duty ratio and the time period. So first of all, is this related to voltage mode control or current mode control?
That how we have to design.
Yes.
Sorry.
Yeah, yeah. So in the case of voltage mode control, the waveform that we'll be comparing is sawtooth. So it will be like a ramp and then step. Whereas in the case of current mode control, we'll be comparing with the actual current, which is
Got it.
triangular. So based on the waveform, we know whether it is current mode control or voltage mode control. Here I have directly discussed current mode control. So in the case of voltage mode control, we'll have sawtooth. Either it is trailing or leading. Whereas in the case of current mode control, we have the inductor current, and inductor current is continuous, right? It cannot have this kind of step, and we know that inductor current is triangular. So that's why from the waveform we can understand whether it is voltage mode or current mode. So can you
Voltage.
guess voltage mode, right?
It is a voltage.
Yeah, yeah. Whether it is trailing edge or leading edge. You have to see whether the sawtooth is trailing or leading.
It is trailing it, right?
Leading.
Trailing edge. Okay, if you have confusion, I'll again show what we have discussed. So it is trailing because the sawtooth is starting at its value lower than the control voltage. So it is trailing the control voltage. So that's why it is trailing edge. If it is starting at a higher value compared to the control voltage, then it is leading edge. So in this question particularly, yeah, question number three, it is starting from a lower voltage and then it is increasing. So it is trailing the control voltage. So that's why it is trailing edge modulation and not leading edge. Is that clear?
Yes.
So now I have given the slope m1 and I am asking the duty ratio as well as the time period. Can you solve? First, start from the time period. That will be easy. So what will be the time period? I have given the slope m1. You know the peak value of the sawtooth. Now we have to calculate the time t. And there is less than a minute. If this meeting ends, kindly join back. We have few more problems. Session is till 6 o'clock. Sorry, 7 o'clock. We'll solve few more problems before we wrap this session. If the meeting ends, kindly join back using the same link. And are you able to access the videos as well as notes that I'm uploading to my YouTube channel and Google Drive?
Yes, yes.
Okay,
Yes,
okay,
sir.
okay, okay. Someone, no, sir. Okay. Jinsi Joy says no. You join the meeting. I'll share you the link in the chat. So let this meeting end. Once we come back, we'll discuss. I hope you can see my screen. So I'm also sharing the links in the chat. You can access whatever I'm uploading, both the videos as well as the notes. Yeah. So coming to our problem, slope m1 is given. I can calculate the m1 in terms of the peak voltage as well as the time period t. So this is my time period t. So I can calculate my m1 as slope, right? So it is height by the base of the triangle. So m1 is nothing but 1 volt by time period t. So now my time period t is nothing but 1 volt by the slope, which is 2 volt per microsecond. So from this I can get my time period as 0.5 microsecond. Is this clear?
Yes.
Yes. Okay. Now
So it
duty
is,
ratio is, yeah. Are you saying something?
yeah, yeah, understood.
Okay. So now the duty ratio is uh, the
T
volt.
on by
Yeah, so this is zero point 0.1, right? So I can see that in a height of 1 volt, for a height of zero point 0.1 it is on, and for a height of zero point 0.9 it is off. So I can say that on time is zero point 0.1 times that of time period, which means T on is zero point 0.1 into T. So I can say that T on is equals to zero point 0.1 times T, which means my duty ratio is zero point 0.1. Clear? I need not even solve. Based on this, I can say, because for overall height is 1 volt and on time height is zero point 0.1. So it is zero point 0.1 times T, and duty ratio is T on by T. So it is zero point 0.1. Is this clear or is there any confusion?
see it is 0.1 into 0.5, right?
Zero point 0.1 into zero point 0.5 is the on time. But I have asked, sorry, but I have asked duty ratio. So anyway, I have to divide it by time period. So my T on is zero point 0.1 into T. So if I calculate on time, so if I calculate on time, my on time will be 0.05 microsecond. You are right. But if I have to calculate duty ratio, I have to do T on by time period T, which is 0.05 micro by zero point 0.5 micro, which is 0.1.
என்னப்பா சூப்பர்
Clear?
நல்லா இருக்கு இன்னும் ஒரு 5 நிமிஷம் அவ்வளவுதான்
Is this clear?
Yes, yes.
Okay. Now let us solve another problem, which is about buck converter. Let me read out the problem for you. Consider a buck converter with an input voltage V in, inductor L, output voltage V naught, and switching frequency is FSW. And we have to find the inductor current ripple for fixed frequency operation, constant on-time control as well as constant off-time control, and we have to find the worst case condition for the ripple current. So what will be the worst case? And in our previous session, week 1, we have discussed that uh, at maximum input voltage, buck converter will have worst case current ripple, means maximum current ripple, but it can vary from different modulation technique. For constant on time it may be different, constant off time it may be different, so we are not sure, we have to check. So can anyone tell me the expression for delta EL for a buck converter? Delta EL expression.
V in into dV in by Fs in L, right?
V in minus V0, right? V in minus V0 into dTs by L, right?
For boost only it is dV in by.
Sorry.
For boost it will be.
Yeah, for boost it is dV in. V in into dTs. Or I can also write it as V in minus V0 into T on by L for constant on time, right? Or I can write V naught into 1 minus dTs if I am considering the off time. Then I will write V naught into T off by L, right? Agree? So I'm writing in different ways because given the problem, whether it is constant on time, constant off time, based on that, I will see, right? So I have to write it in a different way. And let us assume they have not given, assume that V naught is constant. Means we are trying to regulate it at a constant output. So V naught is constant. So if V naught is constant, in the case of fixed frequency, time period is also constant. So V naught is constant and time period is constant. So now I have to write everything in terms of V naught as well as say V in, and then we will check. So the first question, A, time period is also constant. TSC is equals to constant. So now I'll rewrite it in terms of V in everything. So delta IL is V in minus V0. Duty ratio is what? V naught by V in. Time period, if I bring it down, it is L into switching frequency. So if I divide by V in, I'll get V0 into 1 minus V naught by V in by L into switching frequency. Say here in this case, switching frequency is constant. Time period is also constant, and V naught is also constant. So when will be the inductor current ripple maximum? At the maximum input voltage or minimum input voltage?
Maximum input voltage.
Yes, very good. Delta L will be at maximum input voltage because if V in is maximum, V0 by V in will be minimum. 1 minus V0 by V in will be maximum. So this also we have discussed in the last week. So for a buck converter in fixed frequency operation, for a regulated output voltage, delta IL is maximum at maximum input voltage. So whenever we are designing an inductor, for this case, we have to choose maximum input voltage. Now let us go to constant on time control. So I'll use this V in minus V0 into T on. That is what I am going to use. So B, T on is constant. And of course, V naught is also constant in all the cases. So now if I rewrite the expression, I'll get delta IL is equals to V in minus V0 into T naught by L, T on by L. So can you tell at what it will be maximum, at what input voltage it will be maximum? Delta L is maximum or minimum input voltage? T on is constant, V naught is constant. So delta L will be maximum at maximum input or minimum input or at what condition? So someone has texted in the chat. Jinsi Joy says maximum input voltage. Yes. So it is at maximum input voltage. Because if V in is max, V in minus V0 is max. And of course, delta L will be maximum. So for both constant on time as well as fixed frequency operation, delta L will be maximum when input is maximum. Okay. So now let us go to the constant off time control. Constant off time V naught into T off by L, right? Because 1 minus dTs is T off. So let us write C. V naught T off is constant as well as V naught is constant. So what is delta L? V0 into T off by L. So in this case, can anyone comment what will be the case for worst case delta L? Are you following or am I going a little bit too fast? You became silent, all of you.
See, V naught is constant. Vn is not having any role, right? Then how can say that?
Yeah, exactly.
Based on
So
RF.
yeah, very good. So in this case, off time, delta L is independent of input voltage. So if I am fixing the off time, then if I'm regulating at a fixed output voltage, delta L is independent of input voltage. So even if I change the input voltage, ripple will not change. Very good. So that's what I wanted to discuss. In the case of buck converter, delta L is independent of input voltage for constant off time. So depending on that, we can choose the modulation technique as well. Say in some case where we want to attain fixed inductor current ripple and it is say independent of, we want it to be independent of the input voltage, then we can go for constant off time. So similar experimental results sir has provided in a different course, which is digital control in switch mode power converters and FPGA based prototyping. There sir has showed constant on time as well as constant off time implementation live demonstration. So there he has changed the input voltage and showed that how it is varying for uh, constant on time versus constant off time. So in the case of on time, if V in is reducing, ripple is changing. In the case of constant off time, it is constant. So that he has showed in a different course, but here we are learning about the theoretical aspects of the same.
Okay. It is also an NPTEL course.
Yeah, it's a, subsequent course of this. So this is the first
Oh,
course, and this is like a prerequisite for the other course. So in this course, we discuss about all the modulation techniques, controller architectures, small signal modeling, as well as design and simulation. For analog control, in that course, it will be for digital control. So how does the digitization takes place? How the architecture for analog versus digital sampling methods, and then how to choose ADC, and then how to write Verilog code since we are implementing in FPGA, which FPGA we have used, how to use FPGAs and write the Verilog code and dump in the FPGA, and how it can be implemented in hardware. So hardware details are discussed and experimental results are shown. And sir has also showed, I think, a few live demonstration videos. So that is a little bit advanced compared to this course, but you are free to go through that course.
okay. Thank you.
Mhm. So since we are running out of time, I'll try to skip this problem, which is same for the boost converter. I have asked fixed frequency operation, constant on time control, constant off time. Here it is V in minus V0 during DTS. There it will be V in. And for 1 minus dts, it will be v0 minus v in. So only the expression will slightly vary, but the method remains same. And since we are running out of time, I don't want to solve the similar problem twice. So instead, we'll solve a slightly different and interesting problem. This you can do it during your leisure time, but for the time being, I'm skipping that. So now let us go to this problem. Consider a buck converter with the given input voltage as well as output voltage is being regulated, and then on time is 100 nanosecond, I notice 20 amperes. So whether it is constant on time, constant off time, or fixed frequency control.
Sorry.
Whether it is constant on time control, constant off time control, or fixed frequency control.
Constant on time control.
Constant on time, yes. So here on time is fixed, so it is constant on time. And since on time is fixed, time period is varying. So that is the first question. Determine the range of switching time period, and then determine the inductance such that the worst case inductor current ripple is less than 30% of its average value, and calculate the required output capacitance to ensure that the worst case output voltage ripple does not exceed 1% of its average value. So let us start with the problem, means subpart A. So how to solve this? How to calculate the time period? Anyone?
Time period is total
So,
T, right?
yeah, time. Yeah. So basically we have to write time period in terms of the known variables. So let us see how we can do that. We know that V naught is equals to D into V in, and
Yes.
dV in I can write it as dt by T into V in, and dt is nothing but T on by time period T into V in. So now my time period T is nothing but V in by V naught into T on. Clear? I have just written in a way so that I can calculate time period t in terms of the variables that are given in the question. So I have just reframed the expression, known expression for a buck converter. Since V in is given, V naught is given, on time is given, I'm just writing the overall time period in these three variables so I can calculate the range of the time period. So can anyone tell me what is t minimum and what is t maximum? So from here we'll get t minimum as well as t maximum. So what is t minimum and what is t maximum? So all the values are given. You just have to substitute the values and calculate the on time, time period, minimum and maximum.
600 nanoseconds.
Yeah, good. 600 nanoseconds. And then
15 into
1000
100, 1500 nanoseconds.
yeah, very good. So the time period is varying from 600 nanosecond or zero point 0.6 microseconds to 1.5 microseconds. In the case of boost converter, it will be slightly different because V naught is not D into V in. It is V naught equal to 1 by 1 minus D into V in. So it will vary from converter to converter because the relation is slightly different. Okay, now they're asking determine the inductance such that the worst case inductor current ripple is less than 30% of the average value. So 30% of the average value is first of all 0.3 into 20 amperes. So current ripple is 6 amperes. So as we have discussed, at what value or what is the condition such that the inductor current ripple is maximum for constant on time? We have already solved this problem, so that's why I have discussed this part first. So for constant on time buck converter, at which condition is the inductor current ripple maximum?
So value of input.
Maximum value of input, right? Yes. So let us just copy paste this, or I'll copy paste the entire B part. Yep. So I'll have to solve for maximum input and then calculate the inductance at this value. Okay. So my delta IL is given to be 30% of 20 amperes, which is 6 ampere is equals to V in is 15, V naught is 1, on time is 100 nano. So I'll put in nano only, is equals to inductance. So my delta IL should be less than or equals to 6, right? So basically I will say delta IL is less than or equals to 6 ampere because the maximum current should be less than 6. That's what they have given. So now my inductance is greater than or equals to 1400 by 6 nano Henry. So my inductance is greater than or equal to, let me quickly calculate. 1400 by 6, can anyone calculate what is the answer? 1400 by 6. 233.33. Is that what everyone is getting? Hello?
Yes,
Hello?
sir.
Yeah, is this what you are getting? 233.33?
No.
Are you able to follow? Or okay, let me re-explain. For a buck converter, we know that delta IL is V in minus V0 into T on by L. And in the previous problem, we have seen that delta IL is maximum at maximum input voltage. So I have considered the maximum input voltage to design the inductance value L, since that is the worst case. And then they have given the value should be 30% of its average value. Average inductor current is equal to I naught, which is 20 amperes. So zero point 0.3 times 20 is 6 amperes. So that's why I have considered 6. And then I got my inductance to be at least greater than 233.33 nanohenry. So I can choose 240, 250 nanohenry, something like that. Is this clear?
Yes, yes.
Okay. So now coming to the last part, here I'm saying the required output capacitance to ensure the worst case output voltage ripple does not exceed 1% of its average value. So 1% of average value is 1 by 100 into zero point 0.1. So this is basically 0.01 times 1 volt. So the ripple should be 0.01 volt. And I'm not going to derive the expression, but we know that delta Q is equals to C into delta V, and delta Q is nothing but half into delta IL by 2 into time period by 2 T by 2, which is C into delta V. So now I can write it as 1 C is equals to 1 by 8 delta V into delta IL into T. So I always have to consider the worst case, which will result in the maximum capacitance. So I'll also consider delta IL to be maximum. T also should be maximum. So this one I'll consider maximum. This I'll consider also maximum. So that's in that case, I will be designing for the capacitance, the maximum capacitance that is required. Does that make sense?
Yes.
Okay. What is delta IL maximum? Delta IL maximum 6 amperes, right? Hello. This is the worst case ripple, right? At the maximum input voltage, our
Yes,
ripple is
yes.
6 amperes. So my delta IL maximum is 6 amperes. And then I have also calculated time to be how much? T max is 1.5 micro. So this is my 1.5 micro. So this is the capacitance required. So can anyone calculate this value? So let me also calculate. In the numerator, I have 6 into 1.5 micro. Let it be in micro. My denominator 8, 0.01. So I'm getting 112.5 micro. Is anyone getting the same? Hello.
Just 1.11
Yes,
into
yes.
10 power minus 4. Okay.
2.5 micro, because inductance, capacitance are always written in terms of micro, milli, or nano. So we have to convert into the nearest available unit. So I have converted to microfarad. So that's why I have kept the time period in terms of micro only.
Yes, correct. We are getting
Okay.
the same.
Okay. Okay. So is the pace is okay, or are you feeling I'm going bit too fast or bit too slow? Based on your
No,
suggestions, I can improve the next upcoming session.
yeah, if we are going in this speed only, we will be able to see at least 5 to 6 problems, right? So
Yeah.
we
Yeah.
can go in.
We can go
Sir,
bit
one
fast.
request.
Yeah. Yeah.
Sir, one request.
Okay.
Can you make the session by 8 o'clock or 7:30? 7:30 to 8:30. Since we will
Uh,
be coming from office by 6 o'clock, immediately we were not able to sit. That's why I'm asking.
okay.
It's
Okay.
just a request. If it is possible, please make it. Otherwise, no
Okay.
issues.
Okay. I'll check because okay. I'll think about it. I'll also have to communicate with the NPTEL team regarding this. 7:30 to 8:30 may not be possible because that slot may not be there. But I'll check 7 to 8 whether it is possible or not. Would 7 to 8 be okay?
Okay, sir. 7 to 8
Okay.
is okay.
Okay. Okay. I'll check. I'll check. Yeah. And someone was saying regarding the pace. Should I go solve more problems or?
Yes, it will be useful for us if we are solving more problems.
Okay, okay, okay. I'll try to minimize the teaching part because I think I have covered around 20 minutes of the time in teaching. Probably I'll reduce it and solve 2 to 3 problems more. Okay. Yeah, I'll let you know. By next week, I'll see whether I can shift it to 7 to 8, and I'll try to incorporate more time for solving the problems. Yeah. So I'll
Thank you,
just
sir.
quickly summarize what we have discussed today. We have started with the trailing edge PWM as well as leading edge PWM, how it is in the case of voltage mode control, why this nomenclature and how to remember this, what is the logic behind that. Then current mode control as well, trailing edge as well as leading edge. And we have also seen trailing edge is called peak current mode control, leading edge is called valley current mode control. And this is for the fixed frequency modulation techniques. Then we have seen for variable frequency, it is constant on time as well as constant off time, and which of that is valley current mode versus peak current mode control, and one of them is leading edge and trailing edge. We have seen how we can remember this nomenclature logically rather than remembering it blindly. Then we have also seen the hysteresis current mode control. Then we have started solving few problems, starting with the gate pulse generation, how we are getting the on time off time, and how to get the voltage V to generate a particular duty ratio. Then we have solved the RMS current for a inductor waveform. And please remember this formula for the final exam. They might not give the formula. And then we have seen trailing edge. So previously it was leading edge. Now it is trailing edge modulation, and how we can solve for the voltages as well as duty ratio as well as time period in this problem. Then we have seen for a buck converter based on the modulation technique how the worst case inductor current ripple will vary, and we have seen in one of the case it is independent of the input voltage. And we have skipped one problem, and in the final problem we have designed an inductor as well as output capacitor for a buck converter operating in constant on time. See, we will see which is the worst case operating region, and for that case we have solved for the inductance as well as the capacitance. Yeah, so with that, we can end this session here. If you have any questions, you can ask. Else, I'll end this, and I'll try to upload the video by tonight. Yeah, since the class is ending at 7, I'll try to upload it by 8. But if the class is pushed to 7 to 8, then I'll try to upload it by the next day lunch by 1 or 2 p.m. Yeah, Jinsi is also saying more problems, so okay, I'll try to solve more problems from next week. So if you have any questions, you can ask. Else, I'll end this session here. Yeah.
Thank you, Teja. Session
Yeah,
is
yeah. Thank you so
nice.
much. Yeah, yeah. Thank you. Jinsi, thank you. Okay, then.
Session is very nice, sir. Thank you.
Yeah,
Thanks a
yeah.
lot.
Thank you so much. Yeah. And I wish you all the best for assignment too. And we'll meet again in the next week, Monday, preferably 7 to 8. Let us see. I'll contact the NPTEL team.
Okay,
Okay.
sir. Thank you.
Okay. Okay. Okay, then. Good night, everyone. And I wish you all the best.